Hey everyone, and welcome. Today we're going to dive into something that's, well, the absolute bedrock of all science, the art and precision of physical measurement. We're going to see how we actually put numbers to the world around us.
You know, this quote just hits the nail on the head, doesn't it? Without measurement, science, it's just a bunch of interesting ideas, kind of like philosophy. But the moment you can put a number to an observation, that's when an idea becomes a real, testable fact. Everything, and I mean everything, is built on this foundation.
And look, this isn't just about figuring out huge cosmic mysteries. Nope, the exact same principles apply to stuff you see every day. I mean, how long is that tennis table? Or even, how thick is a single piece of paper? To answer even these super simple questions, you need a system, right? You need a standard.
All right, so let's start at the beginning. What actually goes into a measurement to make it, meaningful? It really boils down to two things that have to work together. It's this simple but absolutely critical partnership. Think about it. If I just say, hey, the length is 20, what does that even mean? 20 what? Inches? Feet? Light years? It's totally useless, right? The number, the 20, gives you the how much, but it's the unit that gives it meaning. 20 meters. Ah, now we're talking. That's real information.
Okay, so we've got our number and our unit. But the next big question is, how precise do we need to get? And that, my friends, is where our little quest for the perfect tool begins. Yeah, you can really think of this like leveling up in a video game, but for precision. Level 1, your basic meter rule. It's great for everyday stuff, getting you down to about a millimeter of accuracy. But what if you need to measure, say, the diameter of a pipe? A flat ruler isn't going to cut it. So you level up to calipers. Then, for even more accuracy, you grab the vernier calipers. Boom, 10 times more precise. And for the final boss of tiny measurements, like the thickness of a single wire, you bring out the big gun, the micrometer screw gauge. This thing is an insane 100 times more precise than that simple meter rule we started with. Incredible. So what's the big takeaway here? It's all about choosing the right tool for the right job. I mean, it would be ridiculous to try and measure a room with a micrometer, right? And just as silly to try and get an accurate reading of a wire with a big old meter rule. Every tool has its purpose, its own specific scale, and being a good scientist, or just good at measuring stuff, is all about matching the tool to the task at hand. All right, let's switch gears a bit. We're about to tackle one of the most common mix-ups in all of basic physics. I'm talking about mass versus weight. And I'll give you a little spoiler alert, they are not the same thing. Not even close. So, first up, mass. What is it? Honestly, the easiest way to think about it is that mass is the amount of stuff in an object. It's all the atoms and molecules packed inside you. And here's the really important part. Your mass never, ever changes, no matter where you go. You could be on Earth, chilling on the moon, or floating out in the void of space. The amount of stuff you're made of stays exactly the same. Weight, though, that's a whole different story. Weight isn't about the stuff itself. It's about the force that's pulling on all that stuff. It's basically a measure of how hard gravity is pulling on your mass. And because the force of gravity isn't the same everywhere, it's way weaker on the moon, for instance, your weight can totally change depending on your location. This table here just lays it all out so clearly. You see, mass is the quantity of matter, the stuff. We measure it in kilograms, and it's constant. Weight is a force, the pull. We measure it in newtons, and it totally varies with gravity. Even the tools are different. A beam balance is like a seesaw. It compares one mass to another. But a spring scale, that's actually measuring the downward pull, the force, your weight. And here's the beautiful, simple math that ties it all together. Weight equals mass times g, which is just the fancy term for the acceleration due to gravity. See how that works? Your weight, W, changes because g changes from place to place. But your mass, m, that's your constant. It's always the same. Okay, so we've got length and mass down. Let's move on and quickly cover a couple of other fundamentals, time and volume. Measuring time. I mean, we all get this one, right? And just like with length, the tool you use depends on how precise you need to be. For day-to-day stuff, your watch or the clock on your phone is fine. But when you're in a science experiment or timing a race and every split second matters, that's when you gotta break out the stopwatch. Now for volume, the graduated cylinder is kind of the hero of the chemistry lab. Its main job is simple. You pour a liquid in, you read the marking, and boom, you've got your volume. But here's the really cool part. What if you have something with a weird shape, like a rock?
How do you measure its volume? Easy. You put some water in the cylinder, note the level, drop the rock in, and see how much the water level rises. That difference is the volume of the rock. How cool is that? It's called water displacement, and it's just brilliant.
All right, now for the part you've been waiting for. We've been talking about these super precise tools, the vernier calipers and the micrometer. They look a little complicated, right? But how do you actually read one? Don't worry, we're going to break it down. It's easier than you think. So, looking at a vernier caliper, it might seem a little intimidating with all those lines, but it's really just a simple 3-step trick. First, you get your main reading from the big main scale. That gets you close. Step 2, you look at that little sliding scale at the bottom. Your job is to find the one single line on that bottom scale that lines up perfectly with any line on the top scale. That one perfect line gives you your super precise last digit. And step 3, you just add those two numbers together. That's it. Let's try one out. Okay, so say we look at the main scale, and the reading is just past 4.3 centimeters. So we'll call that 4.30 for now. Then we scan along that little sliding vernier scale, looking for that perfect match. And yep, there it is. The line marked 7 lines up perfectly. So that adds our second decimal place, 0.07. We just add them up. 4.30 plus 0.07 gives us a final super precise reading of 4.37 centimeters. See? Once you do it once, it totally clicks. The micrometer screw gauge? It's pretty much the same idea, just with different parts and even more precision. You've got a main reading on the stationary part. That's called the sleeve. And then you get your fine-tuned reading from the part that you twist. That's called the thimble. And just like before, you just add the two readings together. Simple as that. So let's run through an example here too. The sleeve shows a reading of, let's say, 22 millimeters. Then we look at where the rotating thimble has stopped, and it's lined up with the number 33. That represents 0.33 millimeters. So we add them, 22 from the sleeve plus 0.33 from the thimble, and our final measurement is 22.33 millimeters. That is an incredible level of precision from a tool you can hold in your hand. Okay, so let's wrap this up with a little pop quiz for you. Imagine you're in the lab. You've got a test tube. You need to measure its internal diameter, and you need to be pretty darn accurate. Thinking back on all the tools we just talked about, which one are you going to reach for? And more importantly, why that one? Because making that choice, knowing which tool to use and when, well, that's what good measurement is all about.